can't get my computer stopped working. I'll go into iLearn to get the. Where's it going? All right, this is record low numbers of students, but that's all right. I hope others will catch up. And I think it's a very low number of $79 attempts, so that's all right. Okay. So did you find the online quiz easy or difficult? It's quite a high number of hundreds, but I think most of you made a mistake. Most of you means the class made a mistake at this question here. The RF signal is 10 microvolts and the noise voltage is 2 microvolt. What is the signal to noise ratio? So by definition, the signal to noise ratio is the power of the signal divided by the power of the noise. So if you're given voltage, so if you want to find the power, you need to square it, because power is equal to V square divided by R, or I square R. So the relationship between voltage and power is the square of the voltage. So that'll give you 100 divided by 4. It'll be 25. So I think most people just divided 10 with 2 and got the answer 5, which is wrong. So what signal to noise ratio is desirable? Is it 1 or 100 or 0? What is the desired signal to noise ratio of any signal? 100, yeah. So as high as it can be, right? So you want signal power to be really high and the noise power to be really low. So the signal power to the noise power ratio, which is signal power divided by the noise power, becomes closer to infinite or a very large number. So if you have a very noisy signal, your noise power goes up, so your signal to noise ratio goes down. Did you get it right?
No. Is it 5?
It is not.
It's not.
Okay, my computer has come up now. So. Okay, let's look at the mixer basics once again. So just like last week's nonlinear learning content, this part of the mixer is also quite relatively easy compared to the other parts. And also there is only a few questions that I can ask you for the exam. So this topic would be your easy, like your sure bet for marks, because I can do all the permutation combination, but it's only a few types of questions that I can ask, because otherwise it'll become too complicated. So here we looked at that. If you have a mixer, which we shown here as a multiplier, you give in the RF signal at frequency omega 1 and a local oscillator signal omega 2, and you get the intermediate frequency, which is the sum and the difference of omega 1 and omega 2. Okay, so we found the mathematical basis for that omega 1 plus or minus omega 2 comes from multiplying two sine waves or multiplying two cos waves. So cos A cos B is half cos A plus B and half A minus B. So that's where the sum and difference comes. So in your frequency spectrum, when you have the sum and difference, you can choose either of it by applying a low pass filter or a high pass filter, like that. Okay. So why do we need? So we saw also why we need to do this. So if I want to transmit my sound to like 10 kilometers away, I can transmit my sound. It's in its own frequency, which is maximum is 3000 hertz. 3000 kilohertz. There is an equation between the wavelength and the size of the antenna that you need to use to transmit that frequency. So the size of the antenna is lambda divided by 4. So if you have a 1 kilohertz signal, you can find the wavelength lambda, which is the speed of light divided by the frequency. So that's quite a long number, it's kilometers, and 1/4 of that kilometers. So that means you will need an antenna which is kilometers long, which is not possible, right? So what you do, you translate this voice into a much higher frequency in megahertz or gigahertz, and then transmit it using a small antenna, all small electronics, which is possible. So like your cell phone has an antenna inside. Before it used to have outside, now the antenna is inside, and because cell phone is operating in around a gigahertz frequency, so you can have such a small antenna. And at the receiver side, you can use the mixer and a locally generated frequency of 1 gigahertz to get the 3000 kilohertz voice from that. So my voice is reproduced there, but without having to use a giant antenna. So that's why we call it modulation. So there are different kinds of modulation. If you are in communication engineering, so you will see amplitude modulation or AM signal. So you're familiar with AM radio. I don't know if you're familiar with it. It's not that popular like FM radio now. So AM radio, FM radio, and for communication you use frequency shift keying, FSK, PSK, ASK, a lot of different techniques. So mostly for communication at high frequency. But radio is also a communication, but one way, yes.
So in amplitude modulation, it always concentrating some amplitude, the difference of amplitude, and modulating the amplitude.
Yeah.
But what is the use of frequency there? Is there any carrier? The carrier needs to be frequency or something?
Yes. So each one has its own advantage. So have you listened to AM or FM radio? So what do you notice between the two?
FM is much more clear.
Yeah, and AM is much more prone to noise. So if you are listening to AM radio and a jeep, a truck pass by, you can start to hear noise interference in the AM band. But in FM radio, that is not an issue. So it's more.
Yeah, but in AM, actually the frequency doesn't change.
In AM, the frequency doesn't change. You think that, but it is not the case. So if you look at the frequency spectrum, there is this center frequency where you want to carry the carrier signal, and then you have plus or minus signal modulation too.
And that also happens in AM frequency.
Yes, it does happen in AM frequency as well. So this is the basic. So this is slightly out of scope from going to draw a block diagram for a communication equipment. That's beyond the scope of this unit. But if you look at that, so you have the antenna, it goes to a preamplifier. So antenna picks up the RF signal. So if you're talking about FM, it's around 88 megahertz to 108 megahertz band. So you can't go lower or higher band because there are regulations for spectrum. So you can only use this much for broadcasting. So then the antenna picks up that and preamplifies. So that you get, because the antenna picks up very little amplitude. It's not much strong signal. And once you amplify it, then you give it to a mixer. There are different stages of amplification in there, and change the correct for the non-linearities and things. But it's too complicated. Now you give that to the mixer RF, and you locally generate another frequency, and then you get the information contained in that, which is in the intermediate frequency. For radio, it's 455 kilohertz, which is like a standard for a radio. So you need to change. So you change your information from that RF frequency to the IF frequency. Now you can use low speed electronics to amplify it and hear the voice. Okay. Yes.
Does the preamplifier include the quantization where the amplitude AC signal is converted into the DC part?
No, it doesn't. So that all happens after you get the IF. So, but it's, if any undergrads here, don't worry. It's too high. It's completely different unit. You're talking about communication systems. So my question, just to think, is, so when you tune the channel in a radio, what are you actually tuning? So what are you changing?
Receivers receiving end signal.
Yeah, you see many frequencies here. Which frequency are you changing? Are you changing?
Which matches to the one.
Range, which frequency should I?
Yeah, so but
Match the one which they are sending on.
yeah, you can change low pass filter, but if you don't have that component, you cannot get that 455. For example, so there was a question in the quiz. So if you want to listen to ABC Sydney, you need to tune the local oscillator. So when you tune, you change your dial. What you're tuning is you're tuning this local oscillator, right? Then every time, whatever station you want to listen, you always get 455 at the IF stage. Yeah, does that make sense? Okay, so it's mostly might look repetitive, but there's no harm. So implementing the mixer. So we told you that the non-linearity is what makes the mixer operate, and the best mixer is a square law mixer. So you give a x to this x frequency into the system, x a signal into the system, and the system squares the signal. So make it x square. So why it's that good is because now you have three components, just like we have seen in the last class, and two are the harmonics and one is the product. And the product, can you give me another name for the product? I am what? Is it I am 1, I am 2, I am 3, I am 4? I am 2, yeah, that's right. It is I am 2. because I told you a trick to remember. There are two, omega 1, omega 2, so 2, so I am 2. So if it will be 2 omega 1 and omega 2, that will be I am 3, right? Because 2 plus 1 omega. So mixer also can be implemented by another nonlinear devices where you have the equations like that. So A1 times the signal, A2 times the square of the signal, A3 times the cube of the signal, etc. So in this particular case, you're giving the RF and V local oscillator, VLO, into the input of this system, and you're measuring your output at the load resistor at the output. So when the output, the equation is here, so the equation will be IS times the system's response times the resistance of the load. Okay, same concepts. So you have the fundamental here from the linear component, and the square of the signal, and then the cube of the signal. So when you do problems in the exam and maybe assignment, you just need to be quite focused and not make any mistakes along the line, because there is going to be a lot of terms in there. Okay, that's the only thing. So these are things that you can learn, which is nothing except what we have already looked at. So these are just some expansions, so you can look at that. So usually when you talk about a mixer, you write the output like that, like in a sigma form, sigma n equal to 1 to infinity an vin the whole square. So in this square law device, the top n equal to 2, so it has only two terms, n equal to 1 and n equal to 2. Okay, so you give a signal in, which is the sum of the two signals, the RF signal and the the LO signal, and then you give through this system, that'll give you this plus omega RF plus omega LO the whole square. So that'll give you, this term will give you the fundamental, this term will give you the cross modulation and the square of the signal. So the square is the harmonics, or the second harmonic of that, and the cross is the product, which gives you the sum and different signals of this. Okay, so one way to look at the quality of the mixer is, or one of the performance parameter is the conversion gain, or voltage conversion gain, or the power conversion gain. So that mixer we looked here, so that created three components, as we said: the fundamental, the harmonics, and the mixed frequency. So we have defined the conversion gain as the voltage conversion gain as the voltage of the IF signal, or which is the output, divided by the voltage of the input signal, which is the RF. So we don't really care about the frequency of the local oscillator, because that is in our control. So we can change it. There is no issue of noise because we are generating it locally. So you can be as high, the amplitude can be as high as possible, or as high as we want. So that's not an issue. So the issue is the RF signal. RF has to be picked up by the antenna, which is in the air, it's propagating. You need to pick up using the antenna, and then use it with the local oscillator to give or produce the IF frequency. So that is why the conversion gain doesn't have the ratio of LO into that. So it's always the voltage conversion gain is the voltage of RF, or the amplitude of RF, divided by the amplitude of IF, or the amplitude of IF, or the output, divided by the amplitude of RF, which is the input. So in this case, when you have the total output signal, the sum of these three, you can easily find the voltage conversion gain. So you just need to find what is the coefficient for the IF. What is the coefficient of IF here? So there are 1, 2, 3 terms for. So you all agree that the output voltage is the sum of all these 3 terms, 1 plus 2 plus 3. Which is IF in this? Is it 1 or 2 or 3? 3. Yeah, 3 is the IF because that is the cross product. And the other one, the V square, is the harmonics, right? Because it's the square, which will become 2 LO and 2 RF. They are individually squared, not the square, the whole sum. Okay, they are individually squared here and here, and this is the fundamental. So this is the IF. So the coefficient of IF is this one, and which is the RF. Yeah, that is the fundamental. So this is the coefficient for RF, A1 VRF. So we don't consider LO. And when you find the ratio, you just get this. So you don't have to remember this. So when you are given an input signal, and when you're given an RF and then a LO signals, you just need to add them and square them and see what are the coefficients, and then you find the ratio of the coefficient, and then you get the voltage conversion gain. So if it is power conversion gain, then you square the coefficients. So if it is power conversion gain, then you square the coefficients for both IF and RF, right? So one of the advantages of a square law mixer is the undesirable parts are quite apart in the frequency. So one is so it's easy to filter out. So, and you will notice that there are no higher harmonic terms there. So you found that IM3 was the most difficult to remove because that comes close to the IF, right? And it's really hard to remove them using any low pass or high pass filter. But in this case, there is no IM3 because it's only the maximum power is 2. Yeah. Any questions on that so far? No? All right. It's going to be a short class then. So we have seen in the nonlinear systems, we can use BJT or MOSFETs for making the mixer. And which one made a good mixer? Is it a MOSFET or a BJT? MOSFET, because MOSFET is a square law device. And BJT is an exponential device, and it has that nonlinearity can be expanded into an infinite number of terms with an infinite number of powers. So each power will contribute its own frequency component to the output. While in MOSFET, it's only power 1 and power 2. There is no higher power terms there. So you're done in the lab that the MOSFET outputs are much cleaner when you look at the FFT of that. So MOSFETs are used for making mixers. But here in our lab, when you come back from the break, we will make some mixers in the lab, but we'll be using BJTs to make mixers. So I told you that you can, add those two signals and give it to the system. So how do you actually add it in a circuit? So this circuit here shows one way to add those two signals. So just let us just look at the DC parts. It's a MOSFET here called M1, and that is biased using this gate resistor and V bias, which is a DC bias, and the output is taken at the drain. This is a constant current bias, so I bias is a constant current flowing through that, so which makes the MOSFET on. So now you need to give two signals. One is the RF signal and the other one is the LO signal, so that when it get mixed you get the IF. So you give RF here at the base, which is no, we have done that in the lab, so it's no big issue. You give the sine wave into the gate of the MOSFET. The other input, VLO, you can give it to the source. So what we are actually doing is VGS, or VGS is VG minus VS. We are actually giving the RF to the gate and LO to the source. Okay, so when you, in the equation for ID, it is proportional to VGS minus VT, the whole square, right? So when you look at VGS, it's actually VG minus VS. So there is the difference. So it's either plus or it's either minus. So, but both will give you the same frequency, just the sign is different. Okay. Questions here? Yes.
VRF and V bias, should they be in parallel or in serial?
VRF and V bias, they don't have to be in series or in parallel, because one is DC and the other one is AC, so that they don't so that they don't see each other. There is a bypass capacitor there. So for RF, it goes directly, get applied to there, while when V bias is considered, this is open. Yeah. So same with the LO side as well. Okay. Make it neater. Any questions? Any more questions? That. Yeah. So yeah, good question. So, you know, what can you guess what it might be used for? Yeah. So it's like when you use a capacitor and an inductor, you're choosing some frequency, right? So you have learned that in the previous units that. Now, you have learned that in this class you should use either a low-pass filter or a high-pass filter to select the sum or difference. And here you used a LC signal, LC circuit. So what is the LC circuit? So L is low impedance in DC and high impedance in AC, or high frequencies. The impedance of L is quite high. So the impedance of L is what? L omega. So as omega goes up, the impedance of the inductor goes up, and the capacitor is the impedance of a capacitor is 1 divided by C omega. As omega goes up, the impedance of the capacitor goes down. So there is only a specific region of frequencies at which this will pass the frequency. So that's called a band pass filter, or you can also make a band stop filter using this. So this would look like this. So that's the part of high pass and a part of low pass. So do you see the low pass here? So this is, sorry, this is the high pass. This is the high pass part, and this is the low pass part. And when you combine them, you get a band pass here, the shaded part. So any frequency beyond or above or below that particular frequency gets blocked, and everything else gets passed. So you can choose that frequency, and the frequency is, this is again out of the scope, 1 by 2 pi root LC off. So you, by changing the value of L and C, you can choose what frequency you want this to operate, what center frequency. Okay. Yeah, another way to use it in a more simplistic way is to put them in series. Now we have LO, RF, and V bias in series, so they all added because of superposition theorem. You had a question?
No, I didn't understand this.
Oh, so we want to. So when you have a mixer, you want to give cos omega RF plus RST plus cos omega LOT into that, to the mixer, right? That's when you get the harmonics, the fundamentals, and the IM2 components, which is the mixed component. So here you're doing the same. So if you don't look at the bias, which is the DC bias, you're just putting the RF and LO in series. And when LO is 0, you have RF there. When RF is 0, you have LO there. That sounds like a summer, which is so either this RF or LO, or both. So 1 1 1, 1 0 1, 0 1 1, and 0 0 0. So this is a sum operation there. Right. So and now, of course, you need a bias for that. Without an input, you still need to make the MOSFET operate. With some certain Q point, some particular current flowing. So once you do that, you get the IF signal at the output. So some issues here. So it looks like a very busy figure there. But if you just look at the dark lines here, your RF frequency is there, and your LO frequency is there. And the mixed output, what you want to see is RF minus LO and RF plus LO there. But that's not the only frequencies that will be there. If you have higher powers, you have 2 RF minus 2 FL, 3 RF minus 3 FL, like quite a lot of combinations. Just for fun, can you tell me what IM is this one? Let's name them by IM. Is it? You said this is 2. Huh? What is the IM number, intermodulation number? Yeah, that is 4. What is this IM? 6, 7, 5, 3. That's fundamentals. That's 3. That's 5. That's 7. That's 2. Right? So we want these two. We want the IM2 components, which are the mixed components, omega plus or minus, omega 1 plus or minus omega 2. Okay? Questions? No? Okay, another issue is the isolation. So we will talk about isolation in the next class after the break, but you will see here the LO and RF, they are all connected together. There is a huge interaction between those two signals. And LO is, I mentioned, it's quite strong compared to your RF signal. So you want the minimum interaction between LO and RF. So that is an issue when you work with mixers. The RF and LO and also IF and LO. The IF is the output of the mixer and LO is one of the inputs. So what happens when the input leaks into the output? So you're basically expecting a 455 kilohertz IF output after mixing, but you got your LO into that. So of course we are doing the low pass filtering, but as you've seen in the lab, there is only a limit. If the input signal is quite strong, you can't completely eliminate that. So there'll be always some traces of that signal there, right? So the LO-IF isolation is quite important when it comes to mixers. So we will deal with that in the next class. So here. Okay, so switching mixers also we will see in detail in the next class. Maybe not that much in detail, but maybe we will repeat the same thing. So one way to, so we looked at all these mixers. We looked at bringing two signals and adding them and giving it to a mixer, right? But one of the signal was LO signal, other one was the input RF signal. But the LO signal can be a switch, and still you can obtain a mixing action there. That switch will operate at the frequency, it'll close and open at the frequency of LO. Okay, so that's when you get the IF frequency at the output. So this is a very simple representation of that circuit in this diagram. So your RF is here, you're feeding it in, and your switch, you're operating at a low frequency, and you're taking your output at the load resistor. And what I say, we will see soon, that this is same as mixing action. Any questions? Isn't it a multiplying function here? So when your switch is off or switch is open, you get 0. And when your switch is closed, you get a 1. Right? So you have your RF, let's say it is 1, and your LO. Your output is 1. So if LO is equal to 0 and RF is equal to 1, your output is equal to 0. And your RF is equal to 0, LO equal to 1, still your output is equal to 0. And both 0 is 0. So this is the truth table for a multiplier. So that's why I call it a mixer, because it multiplies these two signals. Okay. Okay. Any questions with that? Yep. What would you choose? As an engineer, if you have to make a mixer, what component would you choose? There's no wrong answers. You can give a wild guess. You can use a BJT, yes. You can use a MOSFET. You can use a relay if that operates at a mechanical relay, if that operates at such a high frequency, but usually it doesn't. Relays have they operate in seconds or milliseconds, but when you look at megahertz, you want something operating microseconds. So you use some high frequency electronics. So plenty of devices that can do it. Anything with a controllable voltage or current into that, like BJTs, MOSFETs, or power MOSFETs. hemmed. So quite a lot of devices there. Yeah. Anything else? No. So why do I think that we can use the switch or switching operation to make a mixer? Because that square wave signal that you give here to operate the switch, that signal is consisted of so many different frequencies, but all odd harmonics here. So a square wave can be expanded into this sine omega t plus sine 3 omega t, sine 5 omega t, 7 omega t, 9 omega t, and etc. Which in general form you can write like this. So that is a sine wave with a plus between a plus and minus 1 volts, okay, with a 0 DC value. But is it what happens here with a plus or minus 1 volt here in this switching operation? So this sine wave that goes from plus 1 volt to minus 1 volt, that swings between plus and minus 1 volt, you have this expression there. So my question is, can you use the same expression for this switch? So what is the swinging between voltages at this switch? 0 and 1, right? And so half of the time it does not operate, and half the time. So you can see that the whole expression became half. So it was 4 divided by pi, and it became 2 divided by pi, but the frequency components are the same. And also there is a DC part now. Why is that? Because here this is operating symmetrically around 0, so there is no DC part. So once you remove the negative part, now you have a DC value, and that DC value will be 1 divided by 2. DC value is not 1 because you need to average it. So half the time it is 1 and half the time it is 0. So the average for the period is 0.5. Yeah. So that's where the half comes here. Okay, and everything else the same. So the same thing. So we get to the higher order components here, with all difference and sum. So with this knowledge, we can implement mixers using different components. Like if you look at implementing with the diode, all you need to do is just have a simple circuit like this. So there is a current flowing, which is ID, which is the diode current, and you know that diode is a non-linear device, an exponential device. So at the input, you're giving it the switching frequency, or LO, and the RF frequency. No, this is given IF, but it's RF. So okay, another thing. So if you want to broadcast, what you give is the IF frequency. You give your low frequency here, and finally you broadcast the RF. But if you want to, on the receiving side, you give RF here, and then you get IF there. So it is interchangeable. So just like saying, let's look at that. So RF and LO. So if you mix them together, you will get IF. LO, IF. If you mix them together, you get RF. Okay? Not just RF, there will be a lot of other components. You can choose which one you want. Any questions there? Yeah. Sorry, what was the?
The symbol is the X cross inside the symbol is Isha, right?
This one?
No, the on the equation, cross and
Multiplication sign.
Ah, yeah.
Is it a mixer?
Yeah, that's a mixer. Sometimes you just use the star. So another way to implement that. So this is a way to implement that using a diode. So this is the simplest way. This is not a very robust way to implement a mixer, because now you have as a big isolation problem between output and input. So your output gets feedback to the input, and also input comes to the output. So there will be interference from the input here, and also your antenna's sensitive electronics can get damaged by the interference from the output. So this is conceptually it will work, but this is not a very practical circuit. So another way is to use a MOSFET. Here we haven't shown the DC bias part. So this is the MOSFET, and at the source you give RF, and at the gate you give LO, which is same as what we saw before, VGS. Here this is G and this is S. VGS is VG minus VS, the same thing. And at the drain you collect the IF. Okay. So this is so that because some people have a lab on Tuesdays, so that's before the next class. So just want to cover this so that you are familiar with what you're doing in the lab. So there are active and passive filters. What we have looked at so far is all passive filters, even though there was an active component, a MOSFET or a BJT or a diode in there. The load was a passive load. So there are active filters here which can achieve a really high conversion gain. So there are three components for a active mixer, as you see here in this figure. So you give RF to a voltage to current converter, and you give IF to a current to voltage converter. Sorry, you give a LO to the current switch, like we did before. Like we did it here, you give the square wave to the gate or the switch, and RF to the voltage to current converter. Can you name a voltage to a current converter? What is a MOSFET? Because MOSFET is a voltage controlled current device. So if you give voltage, you can control current. By changing the voltage input, you can change the current at the output. Okay, so that is a voltage to current converter. So you can give RF as the input to a MOSFET that will affect the current, drain current going through that MOSFET. So that's the V to I converter. Now you have two differential pairs of MOSFETs. So I'm sure you're familiar with the differential amplifiers by now. So you give a differential input. The square wave that you give is a differential input. So when the M2 is on, M3 is off. And when M3 is on, M2 is off. Because you're giving LO into one of the gate and LO bar to the other gate. So this is a digital circuit notation. So if you say A means the signal A. So if you say A bar, it's a complement of that signal. So if your signal is like this, LO bar would look like the 180 degree phase shifted signal, which would be low like this. Okay, so this is 1 and this is 0. So it'll start with 1. So it'll go from, so when LO goes from 1 to 0, LO bar will go from 0 to 1. So one of these MOSFETs are on M2 or M3 all the time. So it's switching, the current is switching between these two. And that's what creates the mixing action. And of course, we need to take the voltage out, and that is taken through the load resistors or the drain resistors, R1 or R2. So yeah, quick look at what your circuit looks like in the mixer lab next, because some people have labs on Tuesday, you won't have time to learn, and so people coming after the lecture, Thursday and Friday, people have a slight advantage, so I just want to make it even. So you can have a look. So it's the same thing happening. You give the RF to the input, the gate, and then you have a differential pair here, and you take the output across the drain resistors. And what is this one? It's an amplifier. It's a common collector amplifier. It's like a buffer. Okay, there. So here, okay, it's 1 hour. I'll take a break, even though our slides are soon gonna end. Well, you can ask questions in that time. 90 seconds break. Yeah, so
in that case, the previous circuit, what we made where we were superpositioning VRF and VLO, how does that work? Because that's an OR gate.
yeah, so that was, you were adding two signals and giving into a square law device where you are squaring it.
How is that the same from VG minus VS when you were giving RF and LO two different input areas? I mean, in this case, VRF and VLO were going in VG only.
Yeah, so either you give it to, so what we need is VGS,
Yes.
right? So you give it in one in VG and the other one in VS. So when you look at VGS, it is this minus this, which is same as giving on both on one side. So you're adding two signals and giving it into the nonlinear device. In that case.
But that is giving you an OR.
That is an OR, yeah. So you're adding cos omega 1t plus cos omega 2t. You're giving that sum into the nonlinear device where it squares. So you get cos omega 1 square and then the cos omega 2 square, then cos omega 1 times cos omega 2. The multiplication is happening inside that nonlinear device. Here, you're actually multiplying, right, yeah. Because this is the multiplier. So LO is a switching frequency, 1 or 0, and RF is an analog signal. So you're kind of sampling that signal every LO time period, which is a multiplication, direct multiplication here. Yes. Yeah.
For this certain circuit in this capacitor and inductor parallel together, I know that there is a certain means that if the these two values in numbers is the same as the parallel that the impedance will go to the infinite.
Yeah, when you have
but-
an impedance is 0, the impedance here is 0, so that means your output is 0.
No, it has the impedance is infinite.
Yeah, so
It's
that's what I said. You get a peak. So when the impedance is high, the voltage you get here is quite high, right? So
Oh,
voltage is I times whatever is the resistance here, right? Or impedance here, I times the impedance.
oh yeah, I get it.
So you have a high output. So either side.
Yeah,
either-
but what happens if the impedance is very high? That we can replace it as an open circuit in some ways.
It's not open circuit. It's
But
still
it's
quite
nearly-
high. It's not high. It's not infinite. It will be like this. So they call it the Q factor. So the height divided by the width
Wait,
is the. You can look at the Q factor.
okay. Okay, actually,
Also, can you please explain the
Q factor.
question of the quiz, the one that went wrong? How did we get 25, the signal to noise?
So signal. What is the definition of signal to noise ratio? That's the power of the signal divided by the power of the noise.
So
So-
we were given voltages here.
Yeah. So how do you? So and also there was a tip, a clue behind.
The relationship between voltage and power, but I couldn't figure it out in the video.
So if you have a voltage, input and output voltage, how do you convert it to power? So if you have voltage V, now decibel is just a way of representing it,
Yeah.
but it's not. So if you have V, if you have voltage V, when you want to find power, this is the formula for power, right? V squared divided by R. So R is the same for the input and output, so it just cancels. So the power is voltage square.
So it was 100 upon the 4.
Yeah, so it'll be 100 divided by 425. Yeah, any more questions? All right, so let's get back to it and finish it quick. So here, the equivalent way of looking at it is what's happening. An equivalent way of looking at this switch is with a mechanical analog for that. And here you know that the current, the voltage to current converter, the current is GM VGS or GM VRF, right? So the current through the drain, the drain current of a MOSFET is GM VGS. Remember that? Or that is by the definition of GM. GM is equal to ID divided by VGS. So ID is GM times VGS. Now here VGS is VRF. So the IRF, or the current because of the RF, is GM times the VRF. And because it's a differential circuit, you can say that half of the time it is at ST, or it is 1 at some time. The M2 is on here. At that time, M3 is off. And when M2 is on, when M2 is off, the M3 become on. So it's 180-degree phase shift. So the total is as you learn from the differential amplifier circuit, so that is the LO here minus the LO here. So that is the differential input, right? LO minus LO bar. So that will give you this ST minus this one, which is like, so the minus is given here to represent the phase shift, which is the shift of half of a time period, which is 180-degree phase shift. So you get a signal which is +1 to -1. Okay, can you see that? Why you get a -1 there? Because when it is 1, it is 0. So when you minus let's call it A and B. When you minus B from A, we get +1. And when A is 0, B is +1. So when you do A minus B, you get a -1. So you double the amplitude. And now you know the equation for this plus a square wave which swings between +1 and a -1. Right? We have seen that before. That is with 4 divided by pi with no DC part. Right? 4 divided by pi cos omega t, and then 4 divided by 3 pi cos 3 omega t, 5 omega t, 7 omega t, etc. So it contains fundamental frequency, third harmonic, 5 harmonic, and so on. And how do you find the output voltage? I told you the output voltage is our IF frequency, or the mixed frequency. So this same as how we found IF voltage, how we found output voltage in all the BJT circuits and MOSFET circuits before. The output is VDD minus ID R1 here, minus VDD minus ID R2. That's the differential output, which is given here. So now you can replace that I1 with the ST. You can replace that with the ST. So you get the output IF RD times this. And this is our LO. This is our RF. So current due to RF and the voltage due to LO the current due to RF and the current due to LO multiplied with the resistor. Right. So that'll give us this component. You can work it out yourself, like on a paper. Just it's all here. Nothing difficult about it. Just need to be careful when you multiply them. So again, we can find the voltage conversion gain by finding the coefficient of IF and the coefficient of RF, right? So which IF is the IF is the output, RF is the input. So the voltage conversion gain is the coefficient of IF divided by the coefficient of RF. So coefficient of IF is, where is it? This one. That is from here. So this is what gives us the mixed output, right? Because that is the product of LO and RF. That's the product term. And you know when you expand it, you get the plus or minus, right? So the coefficient of IF will be the same as the coefficient of this, which is this one. And coefficient of RF is just this one, or this one. So when you divide them, what you get is this divided by the voltage of RF, which is that gone, just the coefficient. I may have said it wrong there. Yeah, the coefficient of RF is RF itself. That's the voltage of RF, right? This just shows IF. So this is entire thing is IF, which is the V out. Okay, let me explain it again. So once you do this switching and giving the RF into this, the input of the gate of this MOSFET, you get IF, which is same as the output, the output voltage. So the entire thing is IF up to quite a large number of terms. So that is this term plus this term plus this term, and sorry, this term plus this term plus this term, and all multiplied together with this RF current. So only this term, cos omega LO times cos omega RF, will give you the mixed output, which will give you omega LO plus or minus omega RF. And the coefficient of that is this. So this is the coefficient for IF. And coefficient of VRF is VRF itself, because you are giving it as the input. So you just need to remove VRF there, and you end up with 2 divided by pi G1 GMRD as the voltage conversion gain for the circuit.
Should the coefficient of the RF or IF is half of what the averages? Yeah.
No, because we are taking,
Because when you expand cos multiplied by cos,
yeah,
it becomes half of it.
yeah, so it became from 4 to 2. So you are right, but it's already taken care. So here it was 4 divided by pi, 4 divided by pi cos omega LO times omega RF. So it will give you half of the coefficient of this one. Because of that half, it went from 4 divided by pi to 2 divided by pi. And now you remove the RF and you get the equation like that. So how can it come in a question? So can you try to attempt this? So if you're given the voltage conversion gain that we derived here, which is G or GV, is equal to 2 divided by pi GMRD. So if the ID is 100 milliamps and VGS is 3 volt, design a mixer with a voltage conversion gain of 100. So design means you just need to find the two resistor values, R1 and R2. What can you tell me about R1 and R2? Like even before starting they should be the same, right? It's quite a straightforward problem. Yeah. Easy. Did everyone get the answer? Is it difficult? Who thinks it's difficult? Okay. So the way to solve is also given in the next slide. So you're given G, you're given everything else basically except the RD, and you just need to use that in that equation. So another question can be, so you have this kind of a circuit where you have a differential pair and you give the LO frequency on one end and the complement of the LO or the 180 degree phase shifted LO on the other MOSFET M2, and the RF is given at the gate of the third MOSFET. So find the frequency components available. So what you need to do, so you know when you subtract VLO minus VLO bar, you get a square wave which swings between +1 and -1, right? And you know how to expand the square wave with that swings between +1 and -1. So that is 4 divided by pi cos omega t plus the third harmonic plus the fifth harmonics and so on. And then the question is what frequency components are available at the output. So what you do, so you know that this is a product of ST, which is this one. So the output is ST times the RF. Okay. So bias, that is not important because that is just a DC, but it will still create more fundamental harmonics because you're multiplying a constant DC with this AC here. So you can include that, but not necessary. You will still find the answers. So cos omega t, cos 3 omega t, phi omega t times I bias plus IRF cos omega RF t. So this is the input that goes into here, the V bias, which is the, I bias, which is the drain current at the quiescent point. And on top of that, you're modulating this drain current at this frequency, omega RF. Your output here is the multiplied, the product of the switching frequency, which you found here, and the RF input. So you will see that you have several frequency components, and you may be asked to list a few in the exam. Yeah. Yeah, so that is the end of the lecture today. We will look at the second part of mixes after the break, and everyone have a good break, and I think it's the good chance to catch up with what you have missed in this unit and the other units. So I'll be still available on my regular consultation hours during this break. How long is the break? Is it 3 weeks? 2 weeks? Okay, I'll be available in that 2 weeks during the consultation hours. You still can come to me. So I've been sending emails to people. So if you got an email, don't worry, and just trying to check what's happening and how are you and things like that. But you can use that as an excuse to come and visit me in my office. All right. Thank you, everyone. Thanks. All good.
Assignment, it's in most of the cases it's written, sorry.
What is time card? I ask you question vacation.
Yeah. And during the consultation hours, Tuesday,
Usually
one,
Thursday.
1, 2, 3.
1, 2, 3. I need to make appointment.
No, just come in.
Okay. Is that timetable on the island?
Yeah, it is on that.
I have a question about the quiz. For the quiz intro, I have so what the quiz master is basically a single quiz. Because at the beginning I think it's delta because delta is no linear circuit element.
Then it could also be a BJT.
Also it is
Yeah, because that's also non-linear, isn't it?
Oh.
The equations is pretty much same as the diode and the BJT equations are same.
so wait. So the simple signal what
Single multiplier. So it doesn't matter how you're going to achieve it. It's basically you need to multiply. Right.
Sir, in the assignment it's written that you need to write your answers to 1 decimal. It's not written approximated to 1 decimal. So should we round off the
Like if
values
it's
or?
0.67.
To one decimal.
Yeah, 1 decimal.
0.67, you write 0.7.
And
So we round it
0.64
off,
will
right?
be 0.6.
Sorry.
So we have to round it off as per the next.
But I don't think you definitely have to. I think if you have a better accuracy answer, I think the system wouldn't reject it. So if the computer is expecting 0.7 and you write 0.67 and computer knows it is 0.67, then nothing will happen to your answer. That is the least condition. So your accuracy should be at least that decimal point. So you can't write 0.67 as 1, 2.
No,
So
big difference.
it's just the
We just have a few questions about the last assignment problems. Are
Do
you
you need to
available?
go somewhere?
no.
Actually, that complicated some.
The last sum, which I think everyone got wrong, the big kilohertz.
Yeah, the dB kilohertz.
Which assignment?
First assignment.
Your assignment.
Ah, dB kilohertz. Ah, yeah,
Where we were finding the gain bandwidth product.
yeah.
Um,
So if you couldn't find it yourself, so you can come to see me.
Okay.
yeah,
Just solve it together.
yeah, I think it will be better because I'm sorry. So you're available during the break, sir, because your consultation hours are actually during our project practice sessions.
I'm mostly available.
Okay,
Maybe.
so we
Alright.
can.
Yeah.
Thank you.
Have a good break.
Okay.
Happy
You
Onam.
too. Have a good break. I don't have breaks.
Oh, yeah.
Happy Onam Day.
Ah, you too. A happy birthday.
Oh, thank you.
See you, sir.
See you. See you. Have a good break. I can't.
の教室嫌だな。
嫌やな。てか合ってる？
でもさ、100のとここんな形あったよな、あの地図では。
じゃあこれじゃあ。
だからさっきちょっと前にグループプランにいつもの教室を通った時は結構いたそこ。
あ、そうなの。まあみんな来るでしょ。
一番目これ
まだ52分やから。
誰かマックの充電器ないですか？
その辺の人だからね。
マック確かに。そうなんか思った。聞こうかと思った。マックがもう13%だったんですけど、これ
いまいちここ。
なんか全部いまいちだよね。
全部いまいちだよ。
なんかこの時代近いな。
お、なんか
どうであかんの今日。
わかるみたいな。なんか俺のが壊れてるだけ。
うちも AFP がやりたいんだけど、逆はいけへんの？携帯から。そうなの？
壊れてたらしい。
あ、
なんで俺らしかわかんない。サボり。全員サボってくる。
Trouble with air conditioning, you always need layers, huh? It's alright, I can probably just find one. Yeah.
あ、生徒そう。
うちらじゃなくて、環境じゃない。環境。
合ってる？
なんていう授業受けてる？
エンバイロメンタル。
あれほら、ちょこちょことか人来るから。
じゃあ合ってる。あのお姉さん。おばあちゃん。
お姉さん。お姉さんにしとこう。私は今。
これでいけんのめっちゃ嫌なんだよ。
前までもさもっとおったよ。
僕らの真面目な側になる。